Okay, so good morning. I haven't checked the midterm yet. Uh, I hope I can check within this week, but if not, then maybe we'll be finished next week, okay? Because I have another courses to be checked. And next week, since I will go abroad for a few days, I think the Wednesday or Thursday class, there will be no class, but I intend to replace with one more TA session. Okay, so Monday you have TA, and then probably Wednesday next week another TA class. So 2-hour TA class. But Friday, I think I will be here. So I think Friday you still have a class like usual. Okay. So last time the partial derivatives. Okay. We talked about from the how to do partials, some implicit partials, also a chain rule, and if you remember, we have the tangent plane, right? But this is we are going to focus on what we call the directional derivative. So it's like it's derivative, but it has a direction. It has like a factor directions. So if we look at this, so the blue one, suppose that is a surface. There is a surface that we are going to observe. The surface is something that usually visualized in our partials. Okay. If you remember what we did in identification of the surface, like we have the ellipsoid, elliptic paraboloid, and something like that. It's actually one representation of how we are going to use a partial derivative. We can make sure, or we can confirm, or even we can create the surfaces using the calculus. Now, suppose that this blue is a surface, okay? And then we have a plane that is cut off the point P. So at this point, we have this red line T. Okay, so we take a closer look here. Okay, so this let's say this line projected to the xy plane as these vectors. Okay. So we call this vector U. And this is the vector which has a direction to go over there. Okay, and it's described as within this triangle with a distance h. Okay, and this is we call the vector U. Okay. So we can see that the point from the P prime, which is P prime, is the projections from P, and then Q prime projection from Q. This line is the same line with the vector U. Okay. So we can write out a vector equations just to make some connection that this line is parallel to this. Let me write vector U as with that. Okay, just to maybe make it a little bit smaller. Okay. Okay. Or we can write, since the distance is a scalar, so we can write h, or maybe let me write h a and h b. A and B is a vector, so you can write U as A, B. Okay. And then suppose that the Z is, let's just suppose that this is the surface equation. and then let the z0 is this one. This is based on the information given. And then remember, okay, let me write the definition of the in limit. So recall that we have partial derivative with respect to x at x0, y0. It means that we have limit sh goes to 0. The difference between partial x and partial y is one will be constant, one will be variable, and then you can switch with the other one. So we can write here the changes are on x. Okay, so it's going to be plus delta or plus h in this case, and the y will be a fixed constant. Okay, and now for partial y, we are going to switch. Okay, so the one that is going to be a constant will be x, so x0, and then the change is on y. That's why when we are partially derive an equation, if we partially derive, for example, the equation has y. Oh wait. So if the equation has x and y, and we want to partially derive with x, then we can treat y as a constant. Okay. Or the same with the, if we did partially derive y, then we treat x as a constant. Okay. So in another word, if we have the, for example, 2x, this is, let's say this is fxy, you have 2x plus 3xy, okay, and then you want to know the partially derived of the with respect to x. Then we derive 2x become 2, okay, and then this one we treat y as a constant, so we just derive the 3x, so 3y. Okay. This is, we say that partially derived with respect to x. That is this application from here, this one. The change is only x, y is a constant. Why is this happening a lot? So back to this h, okay. If h is going to be distance that is described from the x and y plane, then we can write the change in x. We can write the change in x, let's say the x minus x0, will be equal to the HA, and the change in y will be equal to HB, which means this one. This one. Okay. So this will be projection from the P, okay? This one, this one. So if we have xy, x0, y0, this triangle, okay, this distance here, it means that this is y, this is x. So HB is the change in y, HA is the change in x. Okay, so I can write x minus x0 as HA and y minus y0 as HB. Okay, and we can rewrite this. Maybe let me rewrite this as maybe make it can write that x is x0 plus HA and y is y0 plus HB. Okay. Okay, we have these two expressions in which if we are trying to make out those two, so we can write in terms of, let's say, the delta z over h, z minus c0 over h, and this will be f, and then this will be, we can change the x and y with the x0 plus HA, y0 plus HB, minus f, the original point x0, y0, divided by h. Okay. So we can write the expression for z. We can write the expression of z, the change in the z-axis, as the change within this function minus the original point. Okay. Because this is we take z as a function of xy, right? So the change in z is depending on the xy, okay, as I think in the early introduction of partial derivative, okay? So the change in the delta z, we can express within this. This is actually coming from, we can also relate to the definition of the partial derivative itself with limit. So from these expressions, if we take the h as closer to 0, so as this is going to be getting close and close within the limit, then we can write down a new term which we call the directional derivative. Okay. So directional derivative is basically, there are a factor, we define the factor as this AB, which is parallel with the line that is in this surface. So we can write definition as directional derivative with the direction u, or parallel with the factor u, as limit as h close to 0, and then we change the x and y using the expression that we get, that is going to adding some HA and HB, okay? And that's by definition we got that. But what's the implication from this expression? What is the practical application? Which means here we have change in x and we have change in y. Okay. So basically, what this partial, the directional derivative is actually giving you expressions that you can have a partial x and then partial y. Okay. So we can write here. Do I have the paper? Oh no. Okay. Maybe let me just write down here. So as a consequence, or maybe in application, if the f is differentiable function of x and y, we can write, and then f has the directional derivative. Let me write directional derivative of any factor. We say factor u. Let me write here factor u, which has the component a and b for x and y. And we can express the directional derivative as d with subscript u f x y. So this means the directional derivative of factor u of the function of two variables. This equal partial x xy a plus partial y xy b. Okay, maybe still a little bit not really applicable. Let me give you some example. Okay, a quick example. A quick example. So suppose, let me write here example. Suppose that we have the function, let's say x cubed minus 3xy plus 4y squared. Okay. And then suppose that we have the u, the unit vector. Maybe let me write with the sentences. Okay. U is the unit vector in the direction given by angle pi over 6 measured from x-axis. Question is, what is directional derivative at point 1 and 2? So this is a standard question in the directional derivative. So what do we do now is basically describe what is our theta and what does the theta will affect to the vector. Okay, so it means if I draw some, let's say this is, I simply draw, usually the 3D axis is going to be here, but since this has an angle and I want to show the angle, so I will rotate a little bit, so make it z, and then this, the xy is like that. So z will be here, this is y, this is x. So it says that from x it is measured an angle pi over 6. Okay, so let's say the u is this, okay, from here. Let's say this is u. Okay, now the angle will be start from here, right, from the x-axis. So remember, measure from x, so you have an angle here which is pi over 6. So now you have a triangle here. So of course, from this expression here, from this triangle, we can express this x and y in sine and cosine, right? Okay. So here will be cosine theta. And this should be not like this. This is a little bit wrong. Should be that. Okay. The triangle should be like that. This should be parallel with the y, but this is a right triangle. But since it's not flat, I mean it has some angle rotations within our perspective, and this will be sine. So we can write first the formulations. this will be partial x, xy, and for the x is the cosine, and then partial y, sine. Sometimes the example or maybe the question, sometimes giving an angle like that, or maybe just giving some direction directly. For example, it's giving you a vector, like the equation of vector that you can apply directly. Maybe in I, J, like that, and then you can apply. This is for I, this is for J. You can also take that as a description of the unit vector. Okay, and then we can try to solve this. So d u f x y. So partial x, I will directly write 3x squared minus 3y. Okay, and then cosine pi over 6 plus partial y will be negative 3x, right? Negative 3x plus 8y, and then sine. Let me move this a little bit, and then sine pi over 6. Let me shift this graph to be here. Okay, so we can write this as maybe just express the cosine square root of 3 over 2 and then plus, let's say 8y minus 3x. Sine pi over 6 is 1 over 2. And we can factorize this. And then just multiply 3 square root of 3x squared minus 3 square root of 3y minus 3x plus 8y. And then, well, I think we can just plug the point 1 and 2. So x equal 1 and y equal 2. So 3 square root of 3. And then this will be 6 square root of 3. This will be negative 3. Plus 16. Right? So this will be 13 minus 3 over, okay, and then over 2. Okay. Now this is, we call the directional derivative at point 1, 2 with the direction, the pi over 6, the theta equal pi over 6. And remember that the u is a unit vector. Okay, u is a unit vector. You need to define. So if you're given a vector, then you need to find the unit vector. Do you still remember how to find a vector? No. Unit vector, basically. So suppose that you have vector 1 and 2, okay, x, y. Okay. So suppose that this is a vector. So let's say you have a vector 1 and 2, like that. The unit vector is basically 1 over okay. It's basically the vector when the the magnitude is equal to is equal to the but do you know how to get this? Do you remember this? This is 1 plus, oh, not 3, sorry, this is 5. Okay. Unit vector is divided by this. Okay, this is unit vector. The factor divided by its magnitude. Okay, unit vector.
Can you explain how you get like the 3x squared minus 3y and like that minus 3x?
Yeah, it's partial derivative. Here, from this, okay, we derive only to x and treat y as a constant. That's how we do partial derivative. So x cubed becomes 3x squared. 3xy, y is like a regular number. So we just take 3 and then just write y. And y, since we treat as a constant, we make it 0. Treat partial derivative. The same thing with this one. This is for y. Okay, so that is the directional derivative. Okay, now the next thing from this directional derivative is actually this expression here, the whole expression. So let me rewrite the expressions. The original expression maybe on the new page. Okay. So directional derivative has an expression of this is partial x, this is a, and partial y, and this was b. Since a, b is coming from a vector, we can write this in terms of the dot product of these two. So this is actually a result of the dot product of partial x, partial y. So we treat this as a vector and then multiply dot product with a and b. Okay. Or the ab, since we know that this is our vector, we can write that this partial, and we can just write dot with the u. So this is, let me write here if you forget, this is dot product. Okay, now this partial, this factor here, it's what we call the gradient factor. Gradient factor of function f. Okay. Or simply, usually we write as these symbols. The symbols we call the del. You will find many applications of this gradient factor in other courses as well. I think in physics, right? Or no? In electromagnetic, at least you need to write the symbols. Or no? In magnets, don't learn. Okay, to calculate the Lorentz. No. Weird. Should be. Okay. So we can write the duf xy as the del of f xy and then u. This means express the directional derivative of unit vector u as a scalar projection. Vector or the gradient vector on the u. So it means, in simple words, this is the vector we call the gradient vector, but the dot product resulting as scalar. Okay. So what does it mean is we projected this vector within this direction to give us scalar value. So it's resulting in scalar value. And why this becomes important in, especially, let's say the electromagnetic, because if you think about magnetic, it has the magnetic fields. Right? To describe magnetic fields, we can use these vectors to describe magnetic fields. Now the same thing with 3 variables. We can still apply similar approach. Okay, so let me write this the summary of this. If we have 3 variables, for example, okay, for 3 variables, we could have the del of the f. So this is the expressing h axis with all the points x, y, z. Okay, that's the del of f with the information. So f is differentiable and let's say u, or the unit vector u is taken into 3 variable as well. And then the directional derivative of these 3 variable, this will be, we can take the dot product and we can still apply to get the scalar value. Or we can just simply write with the del Okay, another quick example how to apply. If we have a function, let's say x sine y z, find the gradient f and then find the directional derivative of the f at uh, 1, 3, 0 in direction of vector I plus 2j minus k. Maybe let me okay, so let me write here before this. Maybe let me copy here. Okay, that's the same. Okay, so basically finding the del means we are going to find all the partials, okay, within this 3 variable function. So we have a function x sine y z. So first let me just write this as partial x, just to give you step by step for process. Okay. So partial x means that we look at the function is x sine y z. So if we see that this is going to be this partial x, we are deriving x, right? Which means x will be 1 and the other part will be still like, you can treat like a constant. So we write the partial x will be the sine, let me write here sine yz, and partial y. So we are going to derive y. Y is inside the sine, so it's become cosine, right? It's become cosine. Cosine, we have y, but z is still there as a constant, so we write cosine yz, but we have a chain rule, right? So we derive yz as z, right? So it will be xz cosine yz. Okay? So you need to be careful. Whenever you do the partial derivative, you need to think which one you derive and which one is a big constant. Okay? And don't forget the chain rule every time you derive. Okay? The same thing with the z. It's similar to with y. So we will have, now it's become xy, and then cosine, and then still the same yz, right? Okay? Anyone still have problem of getting these 3 components? Okay, right. So you need to be careful, consistent which one is the one that will be derived, and which one is you treat as a constant. Okay. So we get the first one. The second one is finding the directional derivative. So first, we are given that the vector is I plus 2j minus k, or we can write as 1, 2, minus 1. Okay. Now this is the vector. It's not unit vector yet, so we need to describe as a unit vector. So we can describe unit vector v, or if you want to change to make your notes better, so you don't mix within your vector and unit vector, you can write in terms of u. Okay. So unit vector becomes 1 over, we squared and then plus all of this, so 1 plus 4 plus 1, so it's 6, so square root of 6, the magnitude of the vector itself. Okay. I plus 2 j, and then it's minus 1. Okay, so that is the unit vector. Okay, the one that we are going to multiply is the unit vector. And then we take the directional derivative at, or maybe if you want to write one by one, it's okay. Or maybe just taking the directly 130, that is the one that we want to apply. It's basically del f 130 multiply or dot product with the unit vector u. Which gives, if you see from the what we have here, so we have 130. So if we take 0 over, if we take 3 and 0 over here, so it becomes 0. Okay, so 0. We take 130 here. We have 1. This will be 0, and we have this 1. Cosine will be 0. So cosine of 0 is 1. XY is become 3. So it will be 0, 0, 3. Okay, 0, 0, 3. So you put the number inside, you will get this is going to be 0, 0, 3. And dot product with u, so 1 over square root of 6. Okay, and then we have, since this is going to be 0, it's going to be 0, so the only one is on the z part. Okay, so we have negative, or let me write to be clear, this will be the, just to review your memory on the dot product, it is going to be 0 multiply with 1 and then plus 2 or maybe 0. And then minus or plus, let me write plus 3 and then multiply with minus. So since this will be the two component will be 0, so we have just only the right side. Or if you want to rationalize this, this will be 3 divided by 6 is half. So this, oh wait, not 3, 6. And that's the directional derivative. So the directional derivative at the end, the result is it's not a vector, but it's a scalar. But it's described as a vector dot product with the unit vector, which result as scalar value. Okay. I hope you still remember also the cross product or not. Cross product, okay, or not? Cross product. The one you did with the left, right hand, like that. Remember this is or not? That's a cross product. So you have to cross this side to this side, and it's resulting from there. Or okay, yeah. So cross product is give you vectors, but the dot product give you scalar, right? Okay. And then to maximize the directional derivative, so we can write here just a quick note before we end the lecture. So if we have this is our expression for the directional derivative, right? Remember in the dot product, we can express this using the magnitude value with cosine theta. So it's actually giving this expression. If you remember the vector part, we can have that. And the magnitude of unit vector is basically 1. It's basically 1. The magnitude of unit vector is basically 1. So this is actually, we can express this by taking this. And the theta is basically angle between the del and u. Okay. How to make the angle maximum? The maximum of cosine is 1. So angle should be 0, right? Should be 0. So the max value is when theta is equal to 0. Therefore, as a conclusion, because when theta is 0, basically you have the same, or this has the same here, it's the same direction with this one. Okay, so which means maximum value of dd is the magnitude of the del of f occurs when theta equals 0, or in other words, this is happen when the u has same direction with the del. And I think that is for today's lecture. Okay, I think that's it for today.